All right. So let's look at some examples in section 2.9 here. Implicit differentiation. So we got x over y equals sine of x plus y, and we want to find dy dx. So really what we want to do then is we're going to take the derivative of both sides with respect to x. And then anytime we're taking a derivative of something that has a y in it, we're going to attach what? A dy dx, right? And that's basically because of the chain rule. Then we're going to get all the dy dx terms to one side, everything else to the other, right? So if I take the derivative of both sides with respect to x, on the left side, what do I have there? A quotient. So I got to use a quotient rule, right? Which is the bottom one times the derivative of the top one. So the derivative of x with respect to x is just 1. I don't need to attach anything, right? Because it was in terms of x. Minus the top one, x times the derivative of the bottom one. Derivative of y with respect to x is just that, dy dx. Or 1, act like it's okay, and then attach a dy dx. All over the bottom one squared. Now, do I have to attach a dy dx on the bottom? That's a trick question, huh? No, because I didn't take a derivative, right? It's only when you're taking the derivative of something that has another variable in it, right? And then this is going to equal the derivative of the right side. Derivative of sine, you can act like it's okay. Derivative of sine is cosine of that thing, but then times the derivative of what's inside, right? So let me, take it times the derivative of what's inside. So the derivative of what's inside is a sum rule. Okay, derivative of sum is the sum of the derivative. So this is 1 plus, and the derivative of y is just dy dx, derivative of y with respect to x. So we have this. So really what we need to do is we need to simplify a little bit, make life a little bit better. So this is just one thing. I'm going to multiply times each part here. And so on the right, I've got cosine of x plus y plus cosine of x plus y dy dx, right? And on the left, I've got that. And actually what I'm going to do is I'm going to multiply both sides by y squared. Can I do that? I might do that first and then multiply all of that. So then I've also got a y squared on these. Is everybody okay with that if I distribute that y squared through there? Get it out of the denominator. And on the left side, what am I left with? I'm left with y minus x times dy dx. So that equals, these two things are equal. These are a little bit easier. So let's just kind of circle what I got that are dy dx terms. So I've got minus x dy dx, and I've got plus y squared cosine x plus y dy dx. In this case, I'm going to move them all to the right, and I'm going to move everything else to the left. So moving those to the right, I've got adding x dy dx to both sides. So it's going to be x dy dx plus y squared cosine x plus y dy dx. Okay, so getting that on the other side, and then I'm going to get everything else to the left. Then I'm going to take this to the left by subtraction. So it's going to be y, and then minus that term is minus y squared cosine x plus y. Okay, and then what do I do on the right? So I've got a dy dx on each term. This is a binomial. So what I'm going to do is I'm going to take that dy dx and I'm going to factor it out, right? I'm going to pull that out. So I'm going to come up top here and keep going. Hopefully, looks like you can see all that depending on how bright the colors are. But anyway, so factoring that out on the right, I've got dy dx times what's left, which is x plus y squared cosine x plus y. Doesn't look like that's too easy to see there, so I need to get rid of my green. Anyway, and this equals y minus y squared cosine of x plus y. So what do I do to solve for dy dx? I'm going to divide both sides by that. So it's x plus y squared cosine x plus y. on the bottom. So dy dx equals y squared minus y squared cosine x plus y over x plus y squared cosine of x plus y. And then you look at what you have here and can we cancel or reduce or simplify anything? For example, can I cancel the y squared's cosine x plus y? Yes or no? I got a mixed crowd. No, why not? Because I have a plus sign in between. It's not attached by multiplication. Okay, so I can't cancel it. So this is actually the final correct answer. Now we could factor out a y upstairs, right? Things like that. So if you can factor and then get one of the factors to cancel out, that'd be great, but it's not going to help if I write that as y times the quantity 1 minus y cosine x plus y. But if I had, you know, something similar down there where I could pull a y out, then we could cancel the y's. Okay, but anyway, this is good. So this is dy dx by implicit differentiation. So implicit differentiation, act like it's okay. Anytime we're taking the derivative of something that has a different variable than what we're taking the derivative with respect to, which is x in this case. So when you see y's, we're going to attach a dy dx. All good with this? So that's implicit differentiation. It's just a process, but really it's just the chain rule because y is a function of x. So I got to take the derivative of that, attach the derivative of that function of x. And we can do that by just attaching the dy dx because we don't know what the function is. We don't know what y is. It could be any function, right? Okay, so I'm going to look at one more example, and I'm going to say, let's go x cubed plus y cubed equals z cubed. Now I've got 3 variables. And let's say I want to find well, let's just take the derivative of this with respect to t. So I'll just call it dz dt. Okay, so really this is a little bit different look. Now we got a whole bunch of variables, right? Where we've only had 2 variables before. Now we got a whole bunch of them. So don't make this harder than it needs to be. What am I taking the derivative with respect to? T. So I'm going to take the derivative of both sides of this equation, but I'm going to take that derivative with respect to t. Okay? So now, we're assuming that x is actually equivalent to a function of t, and that y is equivalent to a function of t, and that z is equivalent to a function of t. Okay? So basically, you know, like a lot of times we say y equals f of x. Well, we could say, you know, f of t, g of t, h of t if you wanted. But anyway, they're going to be in terms of t. So for example, x could be like t squared and y could be t plus 3 and z could be 1 over t, right? That really, they could be any functions of t. So I'm going to take the derivative of these with respect to t. So what do? We add, the process is the same. You go ahead and act like it's okay, right? So the derivative of x cubed is what? 3x squared, but it's an x, not a what? T. So what do we have to attach? Derivative of whatever the variable is, which is x, with respect to t. So the easy way to remember this, the dt is always the one, that's the one on the bottom there. That's always going to be the one on the bottom when you attach it. And it's going to be the same variable of what you acted like was okay. So the derivative with respect to t of x cubed is 3x squared, but then by the chain rule, we got to attach dx dt. All good? So now we should be able to do the next one. What's the derivative of y cubed? Act like it's okay, it's 3y squared, but it was a y, not a t, so what do I attach? dy dt. And then on the right, taking the derivative of the right side, so here we had derivative of the sum is the sum of the derivatives on the left. and then we had to attach those. On the right, you act like it's okay as well. What's the derivative of z cubed? 3z squared, and then I need to attach what? dz dt. Okay. So, and then of course, what was the question? It said find dz dt. Now, what you're going to end up doing in the problems in 2.9 and 2.10 is you're going to find dz dt when you have other conditions satisfied. And I'm going to be able to figure out what x is, what y is, what dx dt is, and what dy dt is. Okay, but I didn't do that yet. So kind of waiting because I'm getting ahead of myself a little bit because this is more section 210. But if I'm just solving this for dz dt, it's just going to be all of that over 3z squared. And then you can solve it if you know what x, y, z, dx dt, and dy dt are for certain values, right? And then you can figure out what dz dt is. Okay, any questions on that? So this is taking the derivative with respect to a different variable. But you could have multiple variables going on. So it's not just, you know, you learn derivatives with just one variable x, right? F of x equals something in terms of x. And then we've been doing where we have x and y's, right? Got to attach a dy dx and then get all those terms to one side, everything else to the other, factor it out. But then now we could be taking the derivative with respect to a completely other variable. And I'll give you an example. When would we do something like this? Well, when these things are in terms of time, right? That would be an easy one. So two ships sailing in the sea, trying to meet each other at a certain point of rendezvous to sail off happily ever after together. It's like your parents. So, all right, anyway. Are you ready for the next one? All right. Let's see. You want to do a word problem then? Since I did something like that. So number 53, did I do number 53? That's the Statue of Liberty one. Did I do that one in the video? Now, so let's do number 53. What do we got here? We've got an airplane is flying parallel to the ground. I'm going to draw a picture of this. So here's the Statue of Liberty is on the left. I thought I did one with the Statue of Liberty. Maybe that's in the ship flame, right? That should be a red flame. Anyway, so there's Statue of Liberty, red flame, and then she's got a crown too, right? And she's pretty. Okay, Statue of Liberty. And then we got airplane flying parallel to the ground. You're going fast, okay? How's that? Pretty good, not really, but anyway. So we got airplane flying, he's going parallel to the ground. So he's flying that way, or whoever the pilot is. All right, and then basically, so that even parallel to the ground there, at an altitude of 2 kilometers. So the altitude is the height, right? So 2 kilometers, is that more or less than 2 miles? It's less. If you run a 5K race, it's only about 3.1 miles, right? So it's less than 2 miles. But anyway, so, and at a speed of 4.5 kilometers per minute. So this plane has a rate of change and is flying at a speed of 4.5 kilometers per minute. So what is I'm going to call that 4.5 kilometers per minute to the right. Okay. So the question, so that's a little bit more than, or a little bit less than 3 miles a minute. Sorry. Anyway, what kind of rate of change is that? Like, what does that represent? That's a rate of change, right? Velocity, that's its velocity. Velocity is a rate of change. So what would I call that? This is the change in what with respect to what? Change in distance with respect to time. And since I'm going that way, like what do you call the left to right? Shouldn't we just call that X? And we can call the vertical Y to kind of stay with what we normally do. So this would be dx dt. And it's a positive. So if we consider going to the right, In this case, if up is north, which it can't be, because the earth is here. But anyway, but if that's east or whatever, north would be into the board. But yeah, we're not really doing that. But anyway, if we consider going to the right on my picture, the positive direction, then that'd be a positive 4.5 kilometers per minute. So every minute, the plane is going to be another 4.5 kilometers to the right after every minute. So after 2 minutes, it's going to be 9 kilometers to the right. 3 minutes, 13.5 kilometers to the right. So anyway, if the plane was going the other way and going in the negative direction, then that'd be a minus 4.5 kilometers per minute. Does that make sense? So the sign does matter on a rate of change depending on which way you're going. So I'm considering up being the altitude to be the positive direction. I'm going to consider that to be the y direction. And then the question is, if the plane flies directly over the Statue of Liberty, at what rate is the line of sight distance between, at what rate is the line of sight distance between the plane and the statue changing 20 seconds later? So basically, what we're doing is we're looking at 2 points in time. One is the plane is right here directly over the Statue of Liberty, and then the plane's going that way, and then the blue picture is after 20 seconds. Well, okay, so what's the problem? Is there any problem with having 20 seconds? Does that match what we got? No, we have minutes, right? So 20 seconds is equivalent to what? How many minutes? 1/3. So it's 1/3 of a minute, 20 out of 60, 20 seconds out of 60 seconds. Anyway, it's 1/3 of a minute later. We want to know, what's the question? What is the rate, at what rate is the line of sight distance between the plane and the statue changing? We're looking for a distance, so I'm going to use a different color here now. I'm going to use black for this. This is the line of sight, right, from her eyes, right? So the line of sight distance, what letter do you want to call that one? If X is left to right and Y is up and down, what do we call this slant? Because it's got to be a variable, right? Because it changes, because the farther right, the different the distance, right? It's going to be a bigger distance. How about another letter? What other letter did we just use before? Z. How about Z? So we're going to call this Z. So Z kilometers. Well, at what rate, what's the rate of change of Z with respect to time? In other words, what are we trying to find? We're trying to find the change in that line of sight distance with respect to time. Aren't we? I believe we are. Now, what would the label on that be? What would the label of dz dt be? Z is in kilometers, so this is the change in kilometers, right? And D is like a tiny change or an infinitesimal change, so like a 1/10 of a second later or whatever, with respect to time. So, or tiny change in time would be like a 1/10 of a second, which would be a real small change on the plane there. But anyway, so this is per minute, not second, right? Did you say minute? Okay, that's good, because we want to change it over so it matches what was given to us for dx dt. All right, so the question we have here then is, now line of sight distance. Is that, I think I drew this wrong. Okay, so there's okay, I think the book is taking a simplified approach, but if we're looking at her eyes are how far above the ground? Anybody been on Statue of Liberty? I mean, that's probably up like a long way, right? Like a tenth of a mile or something like that. I mean, it's up there, or like maybe it's 2/10 of a kilometer, but it's up in the air, right? So the question is, where's this 2 kilometers going? They're taking it to the ground. So what I really believe they're doing, the line of sight would be, so that'd be a difference. We got to know how tall that is technically, right? And then we got to adjust and subtract. Let's say it's 2/10 of a kilometer to her eyes, then this is going to be 1.8 kilometers above her eyes. So we don't want to do that. Like, I don't think they mean for us to do that. So I think what they say is, hey, I'm an innocent bystander laying on the ground here. At the bottom, and I'm looking up in the air and I see this plane. So I think instead of from her eyes, I think it's from the ground level eyes. But anyway, and then now we have 2, we have Z, and then if this is, if I, like, where am I? Like, what's this distance right here? So we got this height is 2. We got this height is 2. We got kilometers. We have this eye length is Z kilometers, which is changing as the plane flies to the right. And then what would this be? Huh? What letter? It's going to change, right? Because the farther over the plane is, the bigger that number is, right? What letter? Well, yeah, I mean, it's got to be a letter. At any point in time, like we'll have actual numbers, right? But in general, how far to the right is the plane as it's flying? X. Call it X. And can we call it X? So it'd be X kilometers. Does that make sense? Now, why can we do that? Well, if I call where I'm laying down the origin, all right, so this is 0, 0, and then this is over X up 0 at this point right here, right? Over X up 0. So like if I was going with the plane on the ground, like I'm on a scooter or something that's going at the same rate, I'd be directly under it, 2 kilometers under it if I was doing that. But anyway, so it's X kilometers to the right. So I'm going to consider basically if I'm looking at, hey, where's my axis, my coordinate axis, I would be drawing it like this, and then the line of sight is from the origin. So just, you can put your axis anywhere I want. If I wanted the XY axis over where the plane is 20 seconds later, I could do that, but then this would be minus X0, and this would be the origin. I would still have a distance of X. That makes sense? So I don't really care if you put it there, or I'm just going to draw it underneath. If I would have put it under the plane 20 seconds later, then and here's the Statue of Liberty. If I would have put it there and had this be the origin, then what happens is this point right here is left X up 0. I could still have a Z, but this is still a distance of X. This is still a distance of 2, and this is still a distance of Z. So really, you know, it's up to you how you draw the picture. Just make your variables match, right? But anyway, so either one of these would work. I'm just gonna have Statue of Liberty be kind of my fixed point, and the base of the Statue of Liberty be the origin, because I think that's a little bit easier. So now let's go and see if we can do the math and answer the question, right? So, but you know, we're working this out together. So what do we know? Like, do you know any equations? What equations do you know? Pythagorean's theorem, right? So a squared plus b squared equals c squared. So in this case, it's x squared plus 2 squared equals z squared, correct? So the sum of the lengths of the squares of the two smaller sides equals the square of the larger side. And we've known that for 6,000 years, because even the Greeks knew that, right? Pythagoras. Anyway, I wonder what he's doing now. I don't know, but that's why you need to learn as much math as you can while you can. All right, anyway. Yeah, maybe, I would assume he's not like Yoda and still alive. All right, but anyway. What do we got here? What are we going to do now? Well, we could find X. Like, what do you mean find X?
Using the 20 seconds at the top, and then figure out how much of a distance that is.
Okay, so we could do that. Before we do that, I'm going to act like I don't know how to, or don't need that yet. But what am I looking for? I'm trying to find dz dt, right? So how do I come up with dz dt? How do I get that to show up from my equation? What could I do to both sides? With respect to, I can take the derivative with respect to t. Okay, and this is why I just did one similar to that, because I have things like this in here. So what is the derivative of this side? Derivative of x squared with respect to t. Act like it's okay. It's 2x, and then I got to attach a dx dt, right? And then what's the derivative of 2 squared with respect to t? What's the derivative of 4 with respect to t? 0, right? Derivative of a constant with respect to any variable is going to be 0. Okay? And then on the right side, what's the derivative of z squared with respect to t? Act like it's okay. It's 2z, but then attach a dz dt. Okay, now we got to plug in what we know. We know what dx dt is. Dx dt is 4.5 kilometers per minute, right? So this is 4.5. And so anyway, and then z, I don't know z yet, and I don't know x. But one of the students said, hey, we can go find x 20 seconds later, right? So how far to the right? And then if we find x, then what else could we find? So really what I need to find is what? I need to find x, and I need to find z. Because what I want to find, what I'm looking for is dz dt. So dz dt is what I'm trying to solve for. So I need to find x, I need to find z based on the information. So we know how far down the road the plane is, or down the skyline the plane is. So how do we figure that out? What formula do you know? Distance equals rate times time. So if you're not, so anyway, distance equals rate times time, or as I like to do it, I like to use capital letters, and I like to switch. I put time times rate because that's me. D equals TR. Timra. Yeah. See, get it? Timra. Anyway, but fine. We use the first one. Distance equals rate times time. So how far x is the distance, right? To the right, and we're 20 seconds later. So 4.5 kilometers per minute times the time. So I can't put times 20. It's got to be times the minute. So 1/3 of a minute. And then that, by doing that, the minutes cancel and I'm left with kilometers, right? So let the labels do the talking. So the distance, which is actually x, okay, the distance is x to the right of 0, would be 1.5 kilometers, right? Everybody agree? Okay, so that goes right in here for x. This is going to be 1.5 kilometers. And then I've still got the 2 there. And this equals 2 times, can I figure out what z is now? If I know what x is, and I know what this is 2, can I figure out z? I should be able to, right? So this is 1.5, 2. Wouldn't it be like 3, 4, 5? Wouldn't that be 2.5? How'd I get that that's 2.5? So z would be 2.5 kilometers. If you don't believe me, go ahead and do it. So you got 1.5 squared plus 2 squared. So what's this? 2.25 plus 4 is 6.25. Square root of that is 2.5. So you can verify that on your calculator. I just knew 3, 4, 5 is a right triangle. And if I consider a half being one of the units. I got 3 units here, and 4 units of a half makes 2. So 5 units of a half makes 2.5. But anyway, you can verify that. So anyway, so the labels are all going to be the same. Z is in kilometers, X is in kilometers, dx dt is kilometers per minute, right? So ultimately, I'm going to get what I need here, but then times dz dt. Long story short, when I'm solving for dz dt, I know what that label is going to be. It's going to be kilometers per minute, right? So anyway, just do the math. That's 3 times 4.5 is what? 13.5 equals, and then 2 times 2.5 is 5 times dx dt, dz dt, sorry. And dz dt is what I'm looking for, right? So divide both sides by 5. So I'm just taking this equation right here. Divide both sides by 5. 13.5 divided by 5 is what? 27? 2.7, I meant. 2.7. I don't know. Is it? It can't be 27. You're dividing it. It's got to be smaller than 13.5, right? How'd I get that, class? I'm not going to use specific names because I'm going to keep this because we're doing some really good work here. How'd I get that? I didn't divide by 5. I don't know how to do that. I divided by 10. Actually, I didn't do it that way. But if you divide it by 10, you get 1.35 and then double it. It's 2.7. Anyway, what's the label on that? That's dz dt. So what is it? 2.7 what? So Z is in kilometers, T is in minutes. So this is kilometers per minute. Make sure you always label. And by the way, it's a positive, right? Even though I don't have the plus sign, if you don't see a sign, it's positive, right? So what does that mean? What's the physical interpretation of that? As the plane is flying past the Statue of Liberty, the line of sight would be doing what, since it's positive? So the line of sight is increasing, LOS, line of sight is increasing at a rate of 2.7 kilometers per minute. All right, anyway, so I just wrote that out. So the line of sight is increasing at a rate of 2.7 kilometers per minute. All good? So this is a nice word problem example from section 2.9. I do some other videos with examples in 2.10. So make sure you watch all my Blackboard videos and have some fun with word problems. Bye.